So, computer architecture, flash memory. A little bit of background and organization for this talk, like always. We'll be separating this in levels of complexity. So, for those not familiar with it, we generally start with level one, which is a simplest high level approach where we go over the main benefits and advantages of this technology. Then in level two, we'll go into basic reading operations as well as look at different types of flash memory layouts. So basically, two main layouts, NAND and NOR. We'll be exploring their naming schemes and how they can affect the behavior of your memory. And then in level three, we'll really be getting into the most complex parts of NAND, giving a quick overview of how the physics behind it works, and then at the very end, we'll take a quick look at the memory controller that is embedded in your SSDs because SSDs have the particularity of having a quite impressive and important memory controller that takes care of a couple of operations like garbage collection, um, monitoring the wear, and um, and evaluating if certain parts of your memory arrays should be quarantined in order to extend the lifetime of this otherwise quite fragile memory. So let's get right into it with level one. So SSDs, which is the purpose of this talk, but actually flash memory, is also called as solid state drives. It is charge-based memory. So charge-based memory means that the memory value is associated with a certain amount of charge on the bit cell. We'll go into this more in detail later, but as you might recall, if you were there on a previous memory talk, we have another type of charge-based memory that we use in our daily systems, which are the DRAM memory cells. So if you were there, you can bring your knowledge on that talk to this talk and see how going from the simple unified concept of charge-based memory, we can really extend this to different types of memory cells. And yes, this talk is being recorded if everything goes right. So, SSDs, unlike DRAM, which even though they are both a charge-based memory, is a non-volatile memory. What does non-volatile mean? Non-volatile means that when you switch off the device, it is supposed to keep its state, and also once on, it's supposed to maintain its state until put in conditions where it is otherwise supposed to change its state. So this gives us very interesting memory structures because unlike previous structures like DRAM, these have to be extremely stable in order to maintain this non-volatile nature. So there are a couple of different types of memory cells that you find in a modern SSD device, going from 1 to 3 bits per cell. So for a single what I call cell array, I can store 1 bit of data, 2 bits of data, or 3 bits of data. I will not be going into detail on how you achieve this higher storage density per bit cell, but it will only be covering single level cell in this talk. A small disclaimer, just to say that these exist. Okay, so before we actually get into detail, we're first going to build a little bit of background on the understanding of what a normal transistor looks like and how it works. So this is your layout for your classical planar transistor. This is what you would find in your CPU, your GPU, and most of your devices. So you have a couple of different parts. Let me get my pointer here. So this is the general structure. You have something which we'll call the channel here, which is built directly on the silicon substrate, and then you have four other main parts. Something called the gate, which is here, this part, the source, the drain, and an oxide that is used to isolate your gate from your channel. The basic idea behind a transistor is that it acts like a controlled switch. Based on the voltage that we apply on our gate, we can either allow or inhibit the flow of charges, so electrons, between the source and the drain. This would be what you would have in a normal N-doped transistor. And in order to not to maintain a reliability on open closed states, we isolate with an oxide the gate from the channel. So you can consider this like a barrier where charges aren't supposed to leak. And so your electrons usually don't go from here to here and from here to here. Now, the flash cell is a little bit different because instead of having only one oxide, it has two oxides. So you've got one isolating layer and then another isolating here. So here you still have your gate, which we will now call control gate, your source, your drain, and your channel. And here you've got a first oxide, and here you've got a second oxide, and in between, we introduce something else called a floating gate. So this is a type of gate that isn't directly driven from anything, so we can't directly control it by applying a certain field directly. Well, we can't control it directly through here nor through here because these you can consider them to be walls for simplification. And so basically, when you have charges in here, you can consider them to be partially trapped between these two oxides. And the basic idea of the flash shell is to store in your charges here. So the data you would retain, let it be a 1 or 0, the state of the cell is equivalent to how many charges, so electrons, do I have stuck in this floating gate. So that was a very, very high level overview of a flash memory cell. Now let's get more into details because this all seems a little bit vague without any better context. And we'll get right back into it by re-talking a little bit about our basic transistor. So here we had it, so our gate, our oxide, our source, our drain, and our channel. And now let's complexify this view. So here I have a n-doped transistor, so your classical n-doped MOSFET. Don't worry too much about the details. Just this is a better understanding of what it means to be opened and what it means to be closed. So this is my closed transistor. Here I've got my channel, which I will also call a depletion region. And the idea is that I have electrons on my source, I have electrons on my drain, and I would like the electrons to be able to flow between my source and my drain this way, but they can't because here I've got a depleted region. And to put it simply, they would need to exert to have a very, very high energy in order to pass through this depletion region. Think about it like two cats on the islands. Here's your first cat on the first island, and here's your second cat on the second island, and here's the water, so that your cat cannot go through the island. And what you're actually going to create when you turn on the transistor is that you're going to create a bridge by applying how can I put this very simply? By applying a voltage threshold, by applying a certain amount of voltage that goes above this voltage threshold, I am actually going to create a bridge where, thanks to a field effect, my transistors are actually going to create a bridge for them to go from my source to my drain. And so my current is going to be able to flow. And so my switch is opened. And here my switch is closed. And what is important to understand here, if you have only one takeaway, is that if the voltage that is applied on my gate is inferior to my threshold, then I do not open this bridge. And if it is bigger than my threshold, then I open this bridge. And it's kind of a binary. Closed, open. And now, depending on the type of transistor I have, so I've got n-doped and p-doped, I have different voltage thresholds. And the basic idea is, in this case, when I go over my threshold, then my current can go from source to drain. And in the second transistor configuration, which we call the p-doping, then when I am under a certain voltage threshold, then my current is negative. So instead of flowing this way, then my transistors would flow this way. So basically, they're two just different types of transistors where you have positive or negative thresholds, and then you invert the direction in which the charges flow. I hope I haven't lost anyone. This is just general knowledge. The main thing you have to think about is you've got this threshold, and if you go over this threshold, electrons can flow, and if you don't go over this threshold, electrons don't flow. And so the principle we're actually going to play around with is the value of this voltage threshold, because when we are actually going to store additional charges or not on our floating gate, we are going to modify this voltage threshold, so the voltage at which our transistor would switch. So here, let's say I have very, very few charges on my flash cell. Then I would have a different voltage threshold than if I have a lot of charges on my flash cell. And if I have very few charges on my flash cell, if I am storing a single bit, which is what we will assume in the rest of this talk, then this is a 1. And if I have a lot of charges on my floating gate, then it is a 0. And so based on the amount of charges I have, I will be modifying my voltage threshold. And so if I have very few charges, my switching threshold here will actually be much lower. Okay, much is maybe an exaggeration, but will be significantly lower than if I had a lot of charge. This is because to obtain the same channel change, so the building of this pathway between my source and my drain, my programmed gate, so basically my gate that has charges on it, needs a much higher control voltage than an unprogrammed gate. And so the control voltage is the voltage is the charge differential that I would need to apply between my source and my drain. So to put it simply, I put less charge, I have a lower voltage threshold, and I put more charge, and I have a higher voltage threshold. And I'm actually going to measure this by taking a reference in the middle. So my voltage threshold reference value here, and I am going to apply this on the voltage, this voltage on my control gate in order to read. And I'm going to see, okay, is current flowing? In this case it would. Then I know that I had a logical 1. And if current is not flowing because my threshold is bigger than my reference voltage, then the current is not flowing, and so I have a logic 0. And so this is how it would go. So I've got my reference voltage, which is my read voltage here, which is some value between my two threshold voltages. And so in this case, it's bigger than my threshold voltage of 2 volts. So I would have electrons flowing, so I would have charges flowing through my channel, so source to drain, logical 1. And in this case, it's smaller than my threshold voltage, so my transistor does not switch. And so I would read logical 0. And now, this is the basic memory cell. We go further and organize them into different types of memory arrangements. You might have heard of them. They're called NAND and NOR. And we're going to get right into it. So NOR is the kind of memory arrangement where you would have one cell. So this is the representation of your flash memory cell. So you would have your floating gate here in the middle. This second line here would be your control gate. Here would be your source, and here would be your drain. And you can see that I can activate each of these lines through my word line here. And then when I activate something, so I put the voltage read threshold, then the value would be able to flow here through my bit line or not flow through my bit line. And I can address them independently. And we call this a NOR flash. just because it kind of looks like the NOR gate um, that I would normally use to build the NOR gates. How I would arrange my n-doped MOSFETs in order to represent a NOR gate logical configuration. We'll not be looking into detail of how this works. We did this in a previous video. If you're interested, I'm sure someone in the comments can link you to which one it was particularly. So the NOR flash configuration is pretty straightforward. Now, unfortunately, it's not actually the one that we currently see the most. What we see the most and what you're probably using inside your SSD is the NAND configuration. So in NAND, we organize them by something called NAND strings, where all of your cells would be built in parallel to one another. And here again, we're just calling it NAND because it really looks like how we would build a NAND logic gate for transistors. Pretty similar. Now we've got a problem here, is that we can't individually get the value of each of these memory cells because they're not individually connected to anything. So we might just have a problem. And let's say that we're going to look at that just afterwards. Because before that, so I don't really know how I would get this value, but why would I actually want to use this NAND if I can't individually address the cell in the line? Well, because as you might have noticed, inside of NAND, I have much less connections and much less wires than inside of NOR. This means that for a given die area, I would have better capacity with this type of memory than in a NOR. But on the other hand, even though this would result in lower memory cells, in NOR I have a much simpler layout, and also I don't have to go through all of these memory cells if I want to read something, which results in faster reading. Now we're going to see just now how we actually do this reading in NAND. But before we can do that, we have to take a couple of steps back and talk a little bit about how your memory is organized inside your flash. So this is a very, very simple overview of a flash memory array. It's organized in blocks, and inside these blocks, each of these lines here is called a page. And all of the pages inside the block are connected. Now, what if I wanted to read this one? How would I do that? So here is a clearer overview of internals of a block. So here's my block array, and here each of these rows is a page, and then inside each of these pages I have my flash memory cells. They're organized in rows and columns, and at the very end I've got my sound amplifier to amplify the reading on my bit lines. So here I can see that that with one line here I am addressing an entire row. So here, this would be connected to my control gate for an entire row. And something important in transistors is that the electrons basically, that, that will go from the source to the drain are connected to the next transistor source to drain. So if I say that this one is open, then this one can get electrons. And so it too can be open or closed, and this one can get electrons and so open or closed. And now the problem with this configuration is that if this one is open, but this one is then this one can and if this one is closed, then this one will never, regardless of its state, actually get the electrons coming to it. And so whatever it does, it's always going to be going to result in no charges being on its output. And so if I want to actually be able to imprint a state from my on my memory cell, then I absolutely need for the charges to be flowing till into its input, into my source, and I absolutely need the charges coming out of it, so out of my drain, to be carried on by the next um, by the next memory cells. So here, let's say that I want to read word line 3, which we were explaining earlier, is that if I actually want data, want the state of word line 3 to be carried from here to here to here to here to here to here to here, then all of these transistors must be open and must be able to allow current to flow through. And the same goes for all of the ones here. So I have, by design, I require for all of the other transistors to be able to be in a configuration where they allow the flow of charge regardless of their state. And this is exactly what we're going to do. We're going to apply something called the voltage pass threshold, which is a pass-through voltage, which is guaranteed to be greater than any of my threshold voltages, so that whatever the charge that is stored on my memory cell might be, I am guaranteed to not impede the flow of electrons, so that I can read the value of this one, regardless of whatever is happening on the others. So I'm sorry if I went back on this a couple of times, but I hope it's clear. So how would this work? Well, here I have a couple of pages. This means that if I wanted to read this page, my read page, then I would have my my reference voltage here that would be applied, and then I would just simply apply the pass-through voltage on all of the other pages, so that the flow of electrons can simply go through here. And if this one results in the bit cells being closed, then they will simply not allow the flow of charges to the next bit cells. And that way, when I get all the way down here to my buffer, I can actually read the value that was stored on that page. Now, in reality, it's a little bit more complex than that, because I am not going to have the clear-cut zeros and ones. And in order to identify the actual value, I need not only to amplify the reading, but to identify the reading. And so for those that were here for DRAM, yeah, we're going to talk about it again. So in order to identify, this is a very simple representation. So in the perfect world, I would have a very clear-cut value for 0. That would be somewhere here, where for a given reference voltage, I would have a given, sorry, for a given threshold, I would be so a given bit cell logic bit memory value, I would have a given threshold voltage for each state. So for one, I would have 1 point where it's okay, this is the threshold voltage for this value that I'm expected to store in the memory, and this would be a single point for the value I would want to store in memory for 0. But in reality, things are a little bit more complex. So I have this probability distribution function, which here is a nice centered um, distribution, where I will hypothesize that the values associated with my memory bit being 0 are somewhere over this reference voltage, and in the other case, they're somewhere under this reference voltage. And so in order to identify it, I would simply, in my sense amplifier, see, okay, is it bigger than reference voltage? Is it smaller than reference voltage? And then write out 1 or write out 0. Now here I talked about reading, but I never actually, I thought about reading, but never really talked about writing. So I'm going to complexify the model that we saw earlier, and this is really where this technology starts to get complex. So in reality, the oxides, so the isolating oxides between my floating gate and my control gate is much thinner between the channel and the floating gate than it is between the floating gate and the control gate. And this is very important. Um, but before, a little bit of background. So in normal physics, I would consider that if I have a given particle, then and this particle's potential energy, which I've noted EP here, is smaller than the potential energy of a barrier, then my particle can't go through the barrier. But this is actually not true, because in quantum physics, what actually happens is that um, my when my barriers start getting really small, I start to notice that my particle um, behaves like a wave, where the amplitude of the wave is the probability of my particle being there. And my particle doesn't just stop at the barrier. Its probability of going through the barrier decreases exponentially with the length of the barrier. But if my particle's probability and so amplitude is very high at the beginning, then uh, there are configurations where this probability doesn't drop to zero. And so even if its initial energy is smaller than it of the barrier, there is still a non-negligible probability that it goes through my barrier. We call this quantum tunneling. And so in most cases, in normal physics, since the barrier is pretty big, then my probability just goes to zero and I never hear of my particle again. But when my particle is crossing a very thin boundary, then here I can see that this attenuation of its probability of actually being there is proportional to a decreasing exponential that is a factor of k. Well, we'll just say k. So it's basically its energy, and x is the distance that I have to go through here. Okay, I hope you're still with me. And so this phenomena allows us to. So this phenomena is actually really interesting because it allows us to have a situation where if the barrier um, is under certain configurations, then my particles can't go through it. So let's say my particles have a very small amplitude, so a very small potential energy and such a very small potential probability of actually being here, then they would see the probability of going through it going really down, and so they wouldn't be able to go through this barrier, and this would means that my charge cannot leak through this barrier, which results in non-volatile memory. But also we can actually manipulate um, this phenomenon in order to allow us for writing. So the problem is we can't actually change the size of this oxide because it's physically there. I cannot modify the structure of my oxide, so modify itself. I cannot just add atoms inside of my silicon once it's been manufactured. But I can modify the effective channel width. So by effective channel width, I actually mean how my particles will be affected on this channel. This effective thickness um, is can actually be bent in a way depending on the potential energy that exists between two parts of the junction. So another way, so this is a representation. This is not really what happens, but here I can see that I have a high potential energy between my floating gate and my control gate. So I would get this very high potential energy by applying a big voltage differential between both of them. And when I do this, you might remember that I said that the particle wave decreased with the thickness of the barrier it had to go through. You can see here that my barrier just got thinner. This is what we mean when we say that our thickness decreased. And so in this case, um, my particles here would be able to tunnel through my barrier, where and in this case, they would simply be stopped because here it's thicker and here it's thinner. Pretty cool. And so this is the basic idea of quantum tunneling. We have a couple of different tunneling regimes. So here we have the stable regime that we have here, or base regime basically. And then here we have this transitional regime, and which is the regime in which we find ourselves when we're doing reads, and maybe when we're programming adjacent cells, and you might be getting some voltage this on the control on the control gate, disturbing it, and so a little bit modifying in which regime we are. But what really interests us is you can see this goes up really fast, and it's this last regime which we call the um, Forel-Nortim tunneling regime, where I would be in this latter regime, and so my particles would be under a big enough voltage differential, and so a big enough field so that they can tunnel through. And so basically, this would induce my this would induce charges being able to flow through my source and my drain. Don't worry, we're nearly done. So how would I do this? Well, let's say that I wanted to program. So programming means adding charges. So let's say that originally I was in a logical 1 state, so there were very few charges on my floating gate. Um, if I wanted to add charges, then I would apply a very strong positive voltage between my control gate and my channel, which is here. And so this very high voltage would modify this effective oxide thickness. And so I would be creating a current flow that I modelize by Jai in here, which would allow my electrons to tunnel through and end up on my flow gate. And then as a result of this, because I do have a voltage differential, I also have this other J out, where some of them will also maybe tunnel through my control gate, but since this one is much thicker, the probability of them actually going through isn't that high, but they will try. And so the thing is, as a couple of these charges accumulate, the differential in charges that are in here and here will start to equalize, and at what point my flow here and this one would equalize, and the flow would stop. And so here I would have charged my floating gate. Now the problem with this is that you can only add more charge using this method, not remove them. If we want to remove them, we're actually going to have to apply a very strong voltage differential between our source and our drain in order to create a flow, an important flow here. And then we're also going to apply a negative um, gate voltage here in order to invert the phenomenon we previously saw and to push my electrons out. We call this erasing. And the particularity with erasing is that unlike programming, it is much more expensive in terms of its hardware implementation, and because it requires negative voltage thresholds, and it requires me to pump electrons using different circuits. Um, in current implementation, what they actually do is that they build this to different granularities. So what do I mean by this? Well, the idea is that what actually happens in your SSD is that you can add charges at a page level, but if you actually want to erase charges, then you can only do it at a block level. Cost reasons. And And so, what if I wanted to add in charges to one of the bits of my page? Well, I could, because I can program at the page level. But what if now I wanted to remove charges from one page of my cell? Well, I can't, except if I want to actually um, clean my entire block. And this is where something interesting comes in, called the memory manager. So you might remember at the beginning of this talk, I said that SSDs have a quite developed memory management system. And this is one of the reasons of the roles it plays into. So is there something called remapping? Since I can't, I can only erase per block, and I can only add charge. If I want to remove charge, then I need to either erase the entire block, or I could remap the associated um, location of this data to another another page. So I actually have some address differentiation table where I have the physical address of the data. So this is the physical address that your computer would know of, and inside your SSD controller, it has an address of the cell on the device. And so let's say I wanted to erase a bit. Well, instead of doing it per block, I would simply look for a block that is free and that has maybe been erased sometime in the past on um, sorry, I would look for a page that is free, that maybe has been erased on in the past. This could be on another block. I don't really care, and I would write the new value to this new block, and then I would replace in my translation table with the new address, and then I would keep in a separate table all of the older addresses for these pages that were discarded, and we call this a page invalidation table. And I would keep track of all these pages that were invalidated. And once I have enough invalidated page per block, I would do something called garbage collection, where I would look for all the pages in that block that are still valid. I would write them somewhere else in order to not lose the data, and then I would erase the entire block all at once. So this is also very interesting as a mechanism, because I get wear on my device based on the number of programming and erasing cycles I do. So by doing this, I can really try to maximize the number of erase cycles I don't do. So minimize the number of erase cycles I do. And so I kind of hinted to this, but there's another role of your memory controller, which is called wear leveling. So I said I wasn't actually going to talk about the three different types of memory cells, but I am kind of. So here you have your single memory cell in blue, SL, um, SLC, the multiple memory cell. So this is 2 bits per memory cell, MLC, and the TLC for 3 bits per memory cell. The problem uh, with um, with it is you can clearly see that depending on the technology I use, but it is true anyway for all of these processes, my bits have a certain amount of endurance for program and array cycles that in some cases can be really low. I'm looking here at less than 1,000. And so in order to maximize the lifetime of my device, I am actually going to try and spread out as best as I can on which cells I am writing, in order to not always wear out the same cells and not have them lose my data because, well, they're dead, and as well as maximize the lifetime of my device. And as we move to most recent technologies, you can clearly see how this is becoming more and more of an important role for our memory controllers. And, and I promise this is the last one, another last interesting propriety, not the last, but another interesting one, is that my optimal reference voltage will evolve over time. So what do I mean by this? You might remember that I would associate a probability distribution function with each of my values. So he would have been my 0 and here would have been my 1. And so the normalize um, and so the threshold voltage for this value would have been somewhere here with a certain distribution. And so my reference voltage would be somewhere smack in the middle. And so my sense amplifier could simply say, this is this one, this is this one. Now, with wear and tear and aging and how long my data is stored in there and how the adjacent cell have written and how that has affected my state, I have drift where my voltage normalized voltage distributions just drift off and maybe in some cases drift into one another. And so in order to prevent this, I'm actually going to have to allocate and estimate a new reference voltage in order to prevent the number of misidentified bits. So what would this mean? Well, imagine I have my 0 value that has drifted to here. I was still using this voltage reference. Well, maybe the probability of me reading a wrong value with this voltage reference is higher than this one. And so I would want to change reference voltage in order to diminish the probability of me misreading my data. And so one of the other roles of my controller is to model and detect these wear and estimate how this is affecting my memory arrays. So this could be by estimating the drift on reference voltage and also estimating which parts of my memory arrays are starting to induce too many errors, rendering them unusable. And so I have the ability to modify the voltage thresholds as well as quarantine the zones if they induce too many errors. And we can build these models either beforehand or even inside. And generally, it's a complement of there too, where you would build a model and then you would program this model inside of your controller, and it would monitor the evolution and the reliability of the lifetime of your cells, and then adjust various parameters according to that in order to still maximize the lifetime of your disk. And so we have seen a quite interesting example of this very recently with Samsung's new MP 733, which they call the Fade-in Place SSD, which is an SSD that, as you can see it here, they boast a very powerful controller where they claim to have used machine learning in order to build a model of how these memories array would age over time, and so they promise something that is not only very fast but very reliable over a 10-year period. I hope you had I hope you had fun and you learned lots of stuff. And thank you very much for your attention. And if you have any questions, please feel free.